Hi to everyone. In this brief video I will try to respond to a blog written by Kirby Erdner on Sunday, February 22nd, 2009. It was titled The MITE Fight. I honestly cannot compete with Kirby. His writing and computer skills are just way above mine. However, this time, instead of refuting his claims by words, I will complement all his claim by a good brief demo. Kirby starts with his statement. Cubes and bricks are all hexahedra, which are less minimal than a tetrahedra. Cube has 6 faces, where the tetrahedron has only 4 faces. Well, this is what we're talking about in here. That's a tetrahedron. So Kirby says that a cube has 6 faces, of course, 8 corners, 6 faces, but a tetrahedron has only 4 faces, 1, 2, 3, 4, and 4 vertices. And Kirby says that that tetrahedron is actually indeed smaller than a cube, which it is, actually 6 times smaller in this particular case, and that the tetrahedrons would be more suitable as a building blocks, which I totally agree. But let's apply the same analogy of minimality to a tetrahedrons themselves. If we compare 2 different kind of tetrahedrons, but of the same volume, let's say like this and this, we can observe that if one of these tetrahedron has all or most of its surface made up of different kind of triangle, then such a tetrahedron will always be inferior in surface to volume ratio versus a tetrahedron which has all or most of its surface is made up of identical triangle. So for example, here we have, this is a B modulo. This is a synergetics B modulo. And we can see that this particular tetrahedron has all faces made up of different kind of triangles. We see that. These 90 degrees scalene, 90 degree isosceles, and these are obtuse scalene triangles, and so is this one. So every triangle, every surface on this triangle is of different surfaces. Where here we have an octant, for example, and this one has 3 identical surfaces and 1 different surface. Now if these 2 tetrahedrons, just assume, would be in the same volume, then a tetrahedron like this one would be more surface to volume its surface to volume ratio would be way better than this kind of tetrahedron. And then we have, this is the B module, and I'm going to show all 9 blocks. I only have these 3 blocks, and we see that this is a quadri-rectangular tetrahedron, has 1 face of 90 degree, other face of 90 degree, 3rd face of 90 degree, and a 4th face of 90 degree. It's called a quadri-rectangular tetrahedron, or it's called a characteristic tetrahedron by Coxeter. Now this tetrahedron is a little bit better because there is only 2 kind of triangles. This is same, and these 2 are same, so it has only 2 kind of triangles. This one has also 2 kind of triangles, but 3 are identical, 1 is different. And this tetrahedron has 1, 2, that's same, these 2 are same, so that's 1, 2, 3. This tetrahedron has 3 different kind of surfaces. And from my set, these three tetrahedrons, even though they are same in volume, this one, because it has most diverse different kind of surfaces, this one is has larger surface than the rest of them. And of course the B module is absolutely the worst because all the surfaces are just different triangles. So we clearly see that any choice, A or B module or MITE, cannot stand up to any of my three blocks derived from a cube. And by the way, my octant is not only the smallest from my set, but if fused with the other octant, it encloses the maximum volume for the least surface among all infinite number of fused tetrahedrons. And even two fused regular tetrahedrons fall short of this surface to volume ratio. Even two regular tetrahedrons would be inferior, and this is what we're talking about. If I fuse two octants like this, there is no other two tetrahedrons which can be fused if they are volume identical, which would have a better surface to volume ratio than these two tetrahedrons. And that also includes the regular tetrahedron. Now I am sure Fuller did not know that. Obviously they never wrote about it, and they always thought that this regular tetrahedron is some kind of a miracle of nature or something like that. But anyway, if these two would be in the same volume, then this tetrahedron would have a lesser surface than that. As a matter of fact, this tetrahedron could not be beat by any tetrahedron, no matter what kind of tetrahedrons you're going to fuse. So we clearly see that any of these three blocks from my cube are more minimal than any synergetic tetrahedron. MITE is same in volume than a 1/8 regular two-frequency tetrahedron. Now let me show that. I want to do this front of the camera so people see. And we have a quarter regular tetrahedron. Okay, I guess that's big enough. We don't have to do all that. So here is the MITE. Let me show a MITE now. This MITE is composed of two blocks, two double corners, left and right, and this is a tri-rectangular tetrahedron according to Coxeter, because there are three 90-degree triangles meeting at common vertex in here. So 1, 2, 3. You see this is a isosceles 90-degree, and these are scaling 90-degree triangles, and this is also isosceles triangle, but it doesn't have a 90 degrees, but these three faces do, so it's called a tri-rectangular tetrahedron, or also known as MITE.